On a simply supported beam, a single point load right in the center, and the show begins. Engineers know the load is shared, half to each support, simple and fair. But inside, the story gets interesting. The shear force starts at the reaction value and travels steadily from the end to the center, and then it jumps. As if the beam were saying, here's the load. It continues its journey, flat and steady, until it ends at the opposite reaction. Same value, opposite sign. Meanwhile, the bending moment starts at 0 and rises gradually at a rate equal to the shear force. It reaches its peak right in the middle, WL/4, then descends with the same calm, finishing at 0 at the other end. It's just one load, but it leaves a complete trace, because in every structure, the way it resists tells its own story. But what happens if we add another load? The beam remains the same, simply supported, resting in quiet balance, but this time, there isn't just one load, there are two. Point loads, identical, placed symmetrically from each end. The beam doesn't complain, it adapts. The reactions adjust. Half of the total load to the left, the other half to the right. A new balance, but just as fair. The shear force again starts at the reaction value, forming a first step. It moves flatly, and just beneath the first load, it drops. Reaching 0, it continues, calm to the second load, and drops again. Each load leaves its mark with a clean step, like signposts along the way. And the bending moment? The moment. It starts at 0 and rises with a smooth slope, following the positive shear rate. It reaches a peak and holds, it no longer increases. The slope is 0, so the moment stays level. When it reaches the next load, it begins to fall, gracefully, obeying the negative shear slope. There is no chaos, only structural logic, because when the load changes, the story changes too. But the beam, true to its design, always finds a way to carry on. The beam remains there, firm, asking for nothing in return. Now 3 loads visit it, precise, equidistant, like carefully measured steps across its back. Once again, the reactions adjust. There's no confusion, only calculations settling into place. The shear force begins with the first step. Once more at the value of the reaction, it moves forward, then drops, sensing the presence of the first load. It remains constant and drops again, 2 more times. 3 steps, 3 marks of what's happening on the outside. Each section between loads is a tense calm, a brief balance before the next impact. It's in these quiet segments where the beam holds its breath. The loads haven't broken it, but they've reshaped the story written across its length. Strength and flexibility now walk side by side, uncertain of what's next, but prepared. The bending moment again starts at 0, rising swiftly, obeying the slope dictated by the first shear jump. At the first load, it slows, still climbing, but as if it's struggling to reach the peak. It conquers the highest point once again at midspan, WL/2. From there, it begins to fall, first gently, then faster, in sync with the rhythm set by the shear force until it returns to 0. And then, a 4th load arrives, another one with the same rhythm, the same distance, the same weight. The beam receives it without protest. The reactions redistribute, as you already know, half to each side. The shear force diagram gains a new step. 4 now, just like the loads, each with the same height. And the diagram becomes a perfectly symmetrical staircase. The bending moment softens between each load. Now there are 5 segments, each with different slopes, more story, always obeying the cues given by the shear. Because each load is a word, and the beam writes its resistance like structural poetry. Now there are 9 9-point loads, equally spaced, precisely aligned on the same beam that began with just 1. They no longer feel like individual weights. Now they resemble a distributed load, yet you can still feel each step, each point where force enters, and the beam responds. The shear force becomes a flawlessly traced staircase. It advances, it falls, it advances, it falls. 9 steps, all equal, all exactly the same size as the force, all measured, like a mechanical heartbeat. And the bending moment transforms. The straight lines between each load begin to melt into an almost continuous shape, as if the beam were breathing under constant pressure. No more sharp changes, short spans with similar slopes, as if it wanted to bend with grace. The beam doesn't complain, because even as the weight increases, with the right design, the structure manages to endure. And then, they're no longer points. The beam now bears something different. The total load is found by multiplying the intensity by the length of the beam. W times L, simple as that. And as you know, each support bears half. A constant, even pressure, like a weighted blanket stretched from end to end. There are no jumps, no steps. The shear force no longer rises or falls suddenly. Now it gently descends like a calm slope that never ends. It starts high, descends steadily, and right at the center, crosses zero. The bending moment changes too. It curves into a perfect parabola, no peaks or breaks, reaching its maximum right at the midpoint. Everything is continuous, everything flows. The beam no longer receives impacts, it's embraced by a steady pressure, and still, it resists. Because in engineering, it doesn't matter if the load falls in droplets or spreads like rain. The structure always has something to say. Now, the load changes shape once again. It's no longer uniform, it grows. It begins at zero, softly, almost imperceptibly, and ends at its maximum value, like a ramp of weight climbing steadily to its peak. It's a triangular load, light at first, but increasingly dense, increasingly demanding. The shear force is no longer a straight line, it's a curve. It starts high and slowly descends with acceleration, drawing an inverted parabola that tilts more with each step. And the bending moment, more elegant than ever, forms a third-degree curve. It begins at zero, rises slowly, and then climbs rapidly to a maximum that is no longer at the center, but closer to the heavily loaded end. That's where the beam struggles most, where the weight concentrates and resistance is tested. The triangular load doesn't strike, it advances, pushes, demands. And yet the beam responds. Because even when weight increases without warning, a well-designed structure knows how to hold, step by step, curve by curve, as if it could foresee what it will have to bear. And so this journey ends, from a single point load to a curve that rises like the wind. What began as sudden jumps is now made of soft slopes. What were isolated points are now a continuous story of weight and resistance. The beam has changed, but not on the inside. It was always the same. It was the load that transformed, and with it, the diagrams, the stresses, the responses. Each new load, each different shape, not only alters the numbers, it also reshapes the way we think. Engineers don't just draw lines, they interpret the invisible, translate weight into equations, and those equations into structural trust. A beam is not improvised, it's designed to withstand even what hasn't yet arrived. Because behind every diagram lies a silent promise that no matter the shape, no matter the weight, no matter the span, the structure will respond. And as long as there is balance, as long as physics is respected, the beam, like every good idea in engineering, will fulfill its purpose, to resist intelligently. Because that's what engineering is, understanding how a straight line can hold an entire universe of forces, and how, with the right calculation and proper design, a structure not only stands firm, but does so with elegance.